Okay, Antoine, it's 5 p.m. here in Gromov, so you may start whenever you wish.
Oh, thank you. So I put the Jamboard link, and this time it should work, in the chat. So. All right, so let me continue on what I was trying to explain last time. Before that, maybe I want to make a quick summary of what happened last time, because maybe the definition of F structures is something that is a little bit hard to swallow in one gulp. So summary of last time. What we did was to define F structures. And then we explained that collapsed manifolds do have F structures. So that's the existence part of a theorem of Cheeger and Gromov. So whenever you're sufficiently collapsed with bounded sectional curvature, then you have F structures that are non-trivial, positive rank. And on the other hand, you have a kind of converse, meaning once you have an F structure of positive rank, then you can find a continuous family of metrics that is collapsing. So you have this corresponding collapsing construction once you know you have an F structure. So conversely, if there exists an F structure of positive rank, then you can find the collapsing family of metrics. So as the parameter t goes to 0, your injectivity radius goes to 0, and the sectional curvature is uniformly bounded in terms of the first metric, G1. So that's the constructive part. For the reference, so the existence part is Cheeger Gromov, let's see, 1990, and the collapsing part is Cheeger Gromov 1986, actually. Let me try to give you more intuition about these F structures. So if you don't like F structures, just think of F structures as torus actions. In F structures, you might need to go to a finite covering space to get a torus action. But for the sake of this talk, you really just need to think of an F structure as a bunch of torus actions that have some compatibility conditions. So think of F structure as some torus actions. The tori may not have the same dimensions, but they have positive dimensions on U alpha and each U alpha, and the U alphas are open sets that cover M. Of M. Next, we talked about orbits of the F structure, and you can think of those orbits as being the orbits of the torus actions. when I write F orbits, I mean orbits of the F structure. Torus actions. And also there was this term positive rank. So what does it mean for an F structure to be of positive rank? It just means in the context of torus action that the action is effective, that the torus is not fixing any point. Okay. So positive rank just means effective action. And also, last time I introduced the word polarized. Think of polarized as just meaning free action. So free action meaning no element, no non-trivial element of your torus is going to fix a point. Okay. Action. And right, so in this, again, in these lectures, you can just think of F structures as this kind of thing. Moreover, so once you have an F structure on, say, your manifold M, then that divides up your manifold into F orbits. And those orbits are a finite quotient of tori. Okay, so let me write this down. Given an F structure, then M is a partition. So is a union of disjoint orbits. And each orbit is going to be a finite torus quotient. Finite quotient of a torus. And remember, positive rank means that these orbits always have positive dimension, and polarized means that these orbits have the dimension of the torus. Let's see. Another comment is that having an F structure definitely puts some topological constraint on your manifold. In fact, if M admits an F structure, of positive rank, then the Euler characteristic of M is going to be 0. And so that's because, all right, so an F structure is just a generalization of, say, a torus action. If a manifold has, say, free or effective torus action, its Euler characteristic is 0 by some classical arguments. And so now if you have your manifold with an F structure, you can divide up your manifold into open sets in which you have these effective torus actions. And so when you put them together by standard computation, you can compute the Euler characteristic to be 0. Right, so what remains to be done? What remains to be done here is to finish my explanation of this collapsing construction. I started to mention some easy cases in this collapsing construction where you can directly apply this killing field rescaling trick. So now let me say a bit more about that. So, construction. First of all, and maybe I forgot to mention that last time, but you in the proof you start with a metric that is invariant for the F structure. For the F structure. So you want a metric that is invariant for, say, the torus action. What does it mean? It means that the torus action is going to be isometric, an isometric action for your metric. And how do you obtain that? You just use an averaging argument. So by an averaging argument that exists, and so for this metric, all these actions are isometric. That is our starting point. And remember, we encountered those easy cases where things are polarized, meaning the actions are free. Okay. A polarized F structure, so it's say a union of elementary F structures that are polarized. F structures. And then what you want to do is to apply the rescaling trick, apply rescaling trick to each elementary F structure. That's no problem. To each structure, no problem, because again, the killing fields are nowhere vanishing because the action is supposed to be free, polarized. And then you use a cutoff function argument to glue these together. Cutoff functions. I'm going to write down a formula for those who want to see a little bit concretely how it works for the cutoff function. It's not completely trivial. Say you you start with your open set U alpha. So U alpha is one of those open sets on which you can define your elementary F structure. You look at the cutoff function of that form. So it's going to be F invariant. Again, in order to make it F invariant, that just means you make it invariant for the torus action. So you can just average any function, any smooth function, and you will get an F invariant function, right? And you want to impose that F alpha is going to be 1 near the boundary of U alpha, and F alpha is 1/2 inside, U alpha minus tubular neighborhood of the boundary, minus the neighborhood of the boundary. Then you set your function, and that's going to be the real cutoff function, I guess, going to be equal to delta. So it depends on delta, the collapsing parameter, to this power. Okay, so that's a little bit arbitrary choice, but what's important is that so rho is going to be let's see. So rho is going to be delta inside U alpha, and very close to partial U alpha, rho is going to be 0. Sorry, to be 1. So now so the metric G delta, you write it like this. And you can check that this is okay. A remark here. So in the standard rescaling trick where there's only, say, one killing field, all you care about is this tangential part and you rescale by delta square. In the general case, when you, have such cutoff functions, because of F alpha, you need to first rescale your metric by a very large constant depending on delta. But the very large constant is in log, and you're rescaling in essentially a power of delta. So this power of delta is going to be more, like a lot smaller than the log. So at the end of the day, the injectivity radius is still going to 0, even though the diameter is going to infinity. So you can check that using very similar computation as the most classical case of just a killing field, you can check that this is upper bounded and the injectivity radius is going to 0. So you're done. So that's the easy case because all the actions are free. You just apply the rescaling trick. Now, what about the difficult case? It's when the F structure is not polarized. And we just need to focus on the case of elementary F structures, because once you know how to collapse an elementary F structure, you just do this gluing together cutoff function argument to get something for the whole F structure. So I'm just going to explain what's happening for elementary F structures that are not polarized. So when you're non-polarized, the action is not free, and you have some orbits whose dimension is not the dimension of the torus that acts on your open set. And I will give you a proof by example. So I will give you some examples to illustrate what's happening and how to solve the problems. And that's going to be it. So first thing to remark is that indeed you have a lot of non-polarized F structure that exists. It's non-polarized F structure. There's a lot of them. A trivial example, here it is. If you take S1 cross R2, you have natural T2 action, which is given by ST. So this is in the torus. It acts on an element of S1 cross R2 as follows. This is S1 cross R2, and it gives the new element. So as you might expect, you rotate in the S1 direction, and you also rotate in the R2 direction. And clearly, this is not a free action. In other words, it's not a polarized action. And we need to understand how to collapse this kind of metrics using this kind of actions, right? Polarized. So here you might say, well, okay, sure, this T2 action is not polarized, but clearly you have an S1 action, which is free. And so that is a polarized action. So you can apply everything that we said, right? And that's true. So in this particular case, in dimension 3, you do have an S1 action, which is free. Here, early S1 action, which is free. So you could think, well, maybe given any polarized F structure, non-polarized F structure, you could modify it a little bit to make it polarized, and then you apply everything that we said. So unfortunately, that cannot be done because at least in higher dimension, at least 4, you cannot always do that. So if you have a non-polarized F structure, you cannot modify it so that it becomes polarized. So let me give you an example in dimension 4, and it's one of the main examples in this theory of F structures. So in general, one cannot make a non-polarized F structure polarized, meaning you cannot find a substructure that would suddenly be polarized. And remember, in order to give you this example, remember the setup of the last few times we already saw this 3 manifold. It's 0, 1 cross R2, and you identify the boundaries using the rotation of angle theta. Where this is the rotation of angle theta. So that's a nice 3 manifold. It's flat. You put the flat metric on it if you want. And it's diffeomorphic to S1 cross R2. But now consider the following. Consider a continuous collection of such E theta when theta is varying between 0 and 2 pi. And what we want to do next is to glue the 2 boundaries. And now you have a 4-dimensional manifold with 2 connected components as the boundary. And you want to glue these 2 boundaries. So let's think about that for a second. And so here, when theta is 0, the angle is 0, then E theta is E0, which is simply the flat S1 cross R2. All right. And when theta is 2 pi, then actually you have an isometric object. So it's also the flat S1 cross R2. So there's a natural isometry between E0 and E1. And you identify E0 and E1 using that isometry. Okay. Okay, purely isometric. And then what you look at is you define the following closed form manifold. That is defined by M being, so all this family of E theta, but then you quotient by this relation where, let's see, 0x is equivalent to 1 and fx. So f is essentially the identity map. So when you look at that, you say, well, this is the trivial bundle, right? But no, actually, this resulting manifold is not a trivial product. So written like this, it's a little bit confusing. But it is true that this manifold is not diffeomorphic to trivial product. So to say S1 cross R2. So locally, it is indeed an interval times S1 cross R2. So all the slices E theta are diffeomorphic to S1 cross R2. But once you glue it using this identity map, so in these charts, it's an identity map, but actually this four manifold is not a trivial product. That's slightly confusing, I think. But let's see. Yes, so it is true. And in fact, in order to give you an idea of what it looks like, let's look at those cylinders in E theta. So cylinder C theta, that is going to be let's see. Yes, so boundary, say boundary of ball of radius 1. So you are in E theta, and basically you take the boundary of a tubular neighborhood of the central S1 fiber. That gives you a cylinder. Okay, if you look at this cylinder, then you look at the collection now of those cylinders. Such that you quotient it by the equivalence relation. So that's a submanifold of your 4-dimensional manifold. It's a 3-dimensional manifold. And in fact, it's a 3-dimensional manifold, which is a T2 bundle over S1. Over S1 with holonomy around S1 given by this nilpotent matrix. That is just something that can be checked. So I'm just claiming that topologically you have something non-trivial here. And next, I want to show you that this non-trivial 4-manifold carries an F structure, which that's pretty clear. But also the claim is going to be that that F structure is not polarized and it cannot be made polarized. So why does it carry an F structure? Well, you see that this manifold M is locally, in fact, a trivial bundle over R, but it simply has some non-trivial holonomy. So, but locally, you do have T2 action as usual, because locally you're just a trivial product, and all the E theta are diffeomorphic to S1 cross R2. So you can write down M as the union of two open sets, and each UI carries T2 action, where UI is of the form theta E theta, and theta is in an open set of S1, 1/2 of S1. In fact, you need to take a slightly larger open set, but morally, this is what you're doing. And so, okay, so that's pretty conceivable, right? Because locally, you're essentially E theta, and E theta has a trivial T2 action that I described in the first example. Okay, in the first example, I gave the T2 action in the case when theta is 0, but you can imagine that there is a T2 action on each E theta. And so this is what makes the F structure. And the claim is that one cannot modify this F structure, one cannot find the substructure, say, of this F structure that makes it polarized, that makes the action free. Polarized. Because of this non-trivial topology. Because of this non-trivial topology. And the intuitive explanation, I won't give a proof here, but the intuitive explanation is that the first reaction when you want to make something polarized is that you have this T2 action, and so you have two directions, and one direction is free. It's an S1 action that is free. And what you would like to say is, well, for each T2 action, you just choose a direction where the S1 action is free. But if you do that in a continuous way, you will have, because of the non-trivial holonomy, you will have, when you do that for each E theta, and you go around the S1. Remember that M is a kind of bundle, the E theta bundle over S1. So in each E theta, you pick what you think is the right S1 action that is free. And you go around S1, you get a non-trivial holonomy. So the S1 action that you get after one loop around S1 is not the S1 action that you started with at the beginning. So in particular, you cannot find an S1 action on M that preserves the fibers E theta, and that is free. So I'm just going to say, just because of this non-trivial holonomy, when you think hard about this, you realize, oh, maybe there's an issue. The holonomy. But in order to collapse the metric, remember, our goal is simply to find a way to collapse continuously the metric. Maybe we do not need something as strong as a free S1 action. So indeed, that's the case. What you can do, and this is the idea, is that you choose smoothly a choice of free R action in each E theta. Collapse. The idea is to choose smoothly, so continuously in particular, an R action free, which is free in each E theta. So you want this R action, and the R action is going to induce a vector field, right? By differentiation, we get a vector field induced by this R action is not going to be a killing field. It's called K. K is never 0. K is, however, a killing field in each slice. Each E theta, but K is not a killing field. So, right. So, what's the picture here? Just to say it with words. You have your 4 manifold, which is a kind of E theta bundle over S1 with non-trivial holonomy. And so in particular, you have a nice local T2 actions, but you cannot make it an S1 action. However, what you do is you're going to pick in each slice E theta an R action that is free. That's always possible. And by changing the direction of this R action smoothly as theta is going around S1, you can find an R action that is well defined, and that defines a vector field. This vector field is nowhere vanishing, so you hope to apply the rescaling trick to that vector field K. Just rescale the metric along that K. But the problem is that this K is only a killing field when you look at its restriction to a slice. So in any E theta, K is a killing field, but K is not a killing field in the whole manifold. So I'm going to finish then to illustrate what we're doing. So now try to apply the rescaling trick to G using K. And the second idea is that because K is not a killing field, you cannot just rescale, contract the metric in the K direction. You might need to expand the metric in some orthogonal direction in order to compensate for the fact that K is not a killing field. First thing is the standard rescaling thing, which is rescaling the metric, contracting the metric in the direction of your vector field. And what's important here is that you need to expand the metric in the direction that is orthogonal to the slices. To E theta to compensate the fact that K is not a killing field. So it's not a killing field, but at least it is a killing field in the slice E theta. And so in the slice E theta, you can rescale using the rescaling trick, but in the directions orthogonal to the slices E theta, you need to expand the metric. So if your metric is given by that, so sum of 3 metrics, remember that this is the part tangential to slices of the form E theta. Here you're orthogonal to the slices. Then you look at this metric, and so theta plus delta plus pp. So you see that you're indeed rescaling, contracting. So delta is very small. So you're contracting the part tangential to k. GT is the part tangential to your vector field k. And G orthogonal here is the part that is orthogonal to the slices, the theta, theta. And in that direction, you need to expand the metric. And there's some nice compensation when you do the computation that leads you to the conclusion. Check that G delta collapses. If you're interested in the computation, which is very close to the standard rescaling trick, and but a little bit more subtle, you can just look at Cheeger Gromov, the original paper. It's well done. Right, and so this example, to summarize, is an example of a non-polarizable F structure, and we got around that difficulty by saying, okay, you cannot find a real polarization, but you can find a kind of fake polarization and just reply the rescaling trick around that fake polarization. And in general, this can be done. It's a very delicate construction because in general, of course, the structure of local structure of an F structure is not as simple as what I draw here. So in general, in order to apply these ideas to non-polarized F structure, we need to, I'm not going to do that, but let me mention that we need to stratify M into some strata. Into some strata indexed by I, and a strata indexed by I is simply all the F orbits of dimension I, which is equal to I. So remember, when there's a loss of dimension for the orbit, that exactly means that the action is not free, and the less the action is free, the smaller the dimension of your orbit. So you need somehow to decompose your manifold into places where the orbit has a fixed dimension and find those kind of fake polarization and do the rescaling trick. So that's a bit delicate. And to conclude, all right, we have that the sectional curvature is upper bounded, and it's upper bounded again by a constant that depends only on the metric you started with. Moreover, the injectivity radius goes to 0, and we need to be careful because the volume has no reason to go to 0, and in fact, this folds. The volume does not go to 0 in general. And in the proof, you can see that because of the way you rescale the metric, but it is a fact that sometimes you can collapse, but you cannot volume collapse. And that's it for the two theorems of Cheeger-Gromov. So we have existence of F structures, and conversely, if you have F structure, you can collapse. What should I say here? Yes, an important comment is the following. So by the way the F structure was constructed by Cheeger and Gromov, the F structure is a structure that only sees what's happening on the scale of the injectivity radius of your manifold. So, given a metric with sectional curvature bounded by 1 and the injectivity radius is very small, as in the theorem of Cheeger-Gromov. So by Cheeger-Gromov, you have an F structure that corresponds to G. And this F structure is living somehow on the scale of the injectivity radius. Of the injectivity radius of your metric, meaning that the F orbits that we found by Cheeger-Gromov, they have size approximately the size of the injectivity radius. So in that sense, F structures, they're really nice. They kind of characterize collapsed manifold, but they're not enough to have a really good understanding of collapsing manifolds, because F structures, again, are only seeing something that live on the scale of injectivity radius. But when you collapse a metric, when there is a very collapsed metric with bounded sectional curvature, it happens in general that you have many different scales that are collapsing at different rates. So F structures, that's fine, but we will see in the near future that you have this notion of N structures, and N structures, the role of N structures is to describe what's happening at scale 1. So we'll have an understanding of the differential structure, a complete understanding of the differential structure of collapsed manifold at scale 1. Right now, we only know what's happening at scale the injectivity radius. And it makes sense because the argument of Cheeger-Gromov was simply a blow-up argument, right? So you start with a collapsed metric, then you say, well, you can rescale it, you blow it up until you see that the injectivity radius is lower bounded by, say, 1. And then you apply some compactness result to say it's modeled on complete and flat manifolds, and you say blah, 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 you get an F structure. But so this rescaling argument makes you only see what's happening on the scale of the injectivity radius. Right, so that's it for these two theorems. And I want to give you some application of these two facts. So applications that are related to the minimal volume and the essential minimal volume. Existence and collapsing construction. Yeah, so what can we say once we know these two theorems of Cheeger-Gromov? First, I have two applications in mind. First, let's recall the definition of min-vol and S-min-vol. So the min-vol of a manifold is simply going to be the infimum of the volume of M when the sectional curvature is bounded by 1, and the S-min-vol is very similar, but you need to first fix the delta and take the infimum of the volume of the delta thick part. And then you take the limit as delta is going to to 0. And that gives you a number that is upper bounded by the minimal volume. Also remember the gap conjecture for the minimal standard minimal volume of Gromov. So that conjecture of Gromov says if the minimal volume is smaller than a small dimensional constant, then the minimal volume should be 0. And this is hard. But however, for the essential minimal volume, it's a direct consequence of Cheeger-Gromov. Right? Corollary. A corollary of Cheeger-Gromov is that indeed there is a dimensional constant such that if the essential minimal volume is smaller than this constant, then it's already 0. So that's a desirable property, meaning you don't have some accumulation around 0. And the proof of that goes as follows. So let's suppose that the essential minimal volume is very small. Okay, let's suppose you have a manifold such that the essential minimal volume is smaller than delta n divided by 2, where delta n is as in the theorem of Cheeger-Gromov. Then there exists, let's see. So there exists a metric such that the sectional curvature is bounded by 1, and the volume of the the part is less than okay, let me use epsilon for now. I don't know if this is the right constant. So if the essential minimal volume is less than epsilon, then that means there is a metric with bounded sectional curvature, so that for any delta, there is such a metric such that the delta thick part has volume less than epsilon. But if you think about that, so remember that for metric with bounded sectional curvature, big injectivity radius means big volume of 1 volt, and conversely, if the injectivity radius is small, then the volume of 1 volt is very small. And here you have that the volume of the whole delta thick part is very small. And in fact, that means that the injectivity radius of this metric cannot be too big compared to the delta that you chose. Okay. So everywhere, the injectivity radius of G cannot be much larger than delta. But now, if you choose delta to be comparable to the delta n in Cheeger-Gromov, that means that the injectivity radius of this metric G is small everywhere. Say smaller than the delta n of Cheeger-Gromov. So that means that if your essential mean volume was very small, then your manifold carries an F structure by Cheeger-Gromov. F structure. And now you apply the converse of this theorem of Cheeger-Gromov, and you say that now that you have an F structure of positive rank, you apply the collapsing construction, and you get a family of metrics collapsing, that exactly means that the essential minimal volume is zero. By the collapsing construction, there exists a family of metrics collapsing. And in particular, when you look at the definition of the essential minimal volume, that exactly means that the essential minimal volume is zero. Right, so you see that by playing with those theorems of Cheeger Gromov, you get that if the essential minimal volume is small, then you get an F structure. Once you get an F structure, you have a new family of metrics that are collapsing. And so the injectivity radius is going to zero everywhere. So in particular, for any fixed delta, the delta thick part will eventually have zero volume. And that's it. So that's the first application, which is, all right, even though for the minimal volume, you don't understand the possible values of the minimal volume near zero, but at least for the essential minimal volume, it cannot accumulate around zero. And for other values of S min vol and min vol, it's, I think, almost completely mysterious. So we do not have even a vague good idea of what the possible values of min vol or S min vol could be in the real life. So the first day I told you about the simplicial volume, which is this topological quantity. And for the simplicial volume, somehow you can compute it in quite a lot of cases. That gives you that the set of possible simplicial volumes is quite well understood. So for example, in dimension at least 4, the possible values of the simplicial volume is dense in 0 infinity. And but for the minimal volume or the essential minimal volume, it's hard to say. It's hard to say. All right. Second application. The second application is going to be this very strange example of Januszkiewicz that shows that the essential minimal volume and the minimal volume are truly different. Let's call that the Januszkiewicz example. So what is this example? It's a four manifold that is closed-oriented, such that the minimal volume is non-trivial, even though the essential minimal volume is zero. For reference, you can see Cheeger and Gromov in the paper of 86. So what it says is that there exists a four-dimensional manifold that is closed-oriented, such that the minimal volume of M is positive, but the essential minimal volume is zero. And that's going to be the strangest, I think, example of these 4 days about collapsing theory. Let's see. So how do you construct such an object? The idea is going to be to cook up a four manifold that has a non-vanishing signature that will show that the minimal volume is non-trivial. But on the other hand, we will construct by hand almost an F structure of positive rank. Once you have an F structure of positive rank, you saw, as in the proof of the last application, that the essential minimal volume is going to vanish automatically. So that's going to give us an example of a manifold that you can collapse geometrically, meaning the injectivity radius is going to zero everywhere, but the volume cannot be collapsed to zero. There's a definite positive lower bound for the volume if the sectional curvature is unbounded. So how does this example works? you take a 3 torus, okay, given by say 3 different independent angles. A 3 torus acts on C3 in the usual way. So you rotate each coordinate of C3 independently. There's a diagonal in T3 that is given by the S1, where you're turning all the coordinates by the same angle. So that gives you the diagonal. And the quotient of T3 by its diagonal is a 2 torus. It acts naturally on actually CP2, because CP2 is nothing else than the unit sphere in C3 that you quotient by the diagonal, actually. Yes, by the way, so this example, you can find it in Cheeger Gromov, but somehow this paper of Cheeger Gromov is riddled with typos for some reason. And in this example alone, I counted 7 typos. So it's pretty, I don't know what they did. So it's a lot of typo, but the math is obviously correct. Let's continue with this example. So you have this action, and it's not a free action. It has in fact 3 fixed points. Fixed points that I'm going to write down. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you have CP2, you have a T2 action on CP2. It's not a free action. You have those fixed points. So the idea is, okay, you remove 3 balls. So you remove neighborhoods of these 3 points. You get a manifold with boundary. You double it, you get a closed manifold. And that's more or less going to be our manifold. Okay. So let sigma 1 be CP2 minus balls around those fixed points, those 3 fixed points. So it's CP2 minus 3 balls. And then let sigma 2 be a copy of sigma 1. And you want to identify the boundary using a given diffeomorphism. So glue sigma 1 to sigma 2 along their boundaries using, for example, so in coordinates, for instance, around 1, 0, 0, you want to use the following identification. It doesn't really matter for us. You just need to reverse the orientation so that the resulting closed manifold is well oriented. So you get M. M is the gluing of sigma 1 with sigma 2. It's an oriented manifold. Is oriented. And it has T2 action on sigma 1 and sigma 2, so they glue together to give an F structure on M. F structure of positive rank. And so because it has an F structure of positive rank already, you can collapse it. So the essential mean volume is automatically 0. But, so by Cheeger. On the other hand, if you look at the signature, this is the signature. The signature is this topological invariant that is defined using the second cohomology group, okay, of your manifold. Anyway, it can be computed when you have a decomposition of your manifold into several pieces. It's additive, actually. So you have that the signature of M is 2 times the signature of sigma 1, which is equal to the signature of sigma 2, which is, okay, equal to, you remember sigma 1 is nothing else than the projective space to which you remove 3 balls. So the signature of sigma 1 is the signature of CP2 minus 3 times the signature of a 4 ball. But the signature of a 4 ball is 0. And so you have that this is just the signature, 2 times the signature of CP2, which is 2. In particular, it's positive. And so in particular, the minimum volume of M is positive. That's really weird. Remember that since the signature can be expressed as an integral of a polynomial in the curvature, that means that the minimum volume is lower bounded essentially by the signature, right? Yeah, so that's why the minimum volume is not 0. The volume cannot go to 0. On the other hand, it has an F structure. In particular, its Euler characteristic is 0, and it has 0 essential minimum volume. Right, so when studying, say, the minimum volume, there's something very delicate happening in the collapsing part. You don't know if the collapsing part is actually not carrying a lot of volume in general because of that example. And you can modify this example to cook up manifolds of any dimension multiple of 4 first. And also you can make it so that the essential minimum volume is still 0, but the minimum volume is as large as you want, simply by gluing more of these sigma 1 if you want. Let's see. So I still have something like 20 minutes. I'm almost done. I'm actually done with F structures. And so I'm going to start the 3rd section, which is about N structures. And in this section, I'm not going to give you really proofs. It's going to be quite impressionistic. The goal is to just understand the statement, and that will be good enough for us. So collapsing theory, this. What about N structures? To prepare you, say a little bit. So N structures are going to generalize F structures. And simply speaking, again, F structures detect something on the scale of injectivity radius, but N structures, it's much, much better because it gives you the geometric structure on the scale of 1 ball. So if you have a manifold with bounded sectional curvature, which is very collapsed, then you can find an N structure living on the scale of the 1 ball. So F structures only see things at level of the injectivity radius. And the problem that is going to be solved by N structures is what's happening at scale 1? What's the smooth structure? Let me give you first a trivial example to show that indeed you need to care about different scales. There's a trivial example, which is you have Tn, which is equal to S1 cross S1. So you have this product of spheres, and you're going to rescale the different, S1s, and you're going to rescale those different circles at different speed. All right. Rescale. You have the flat metric, and you rescale each factor at a different speed. Let's say different speed. So what you can do, yes. So for example, look at S1 of radius, say epsilon times S1 of radius epsilon n. So as epsilon is going to 0, the different factors will have very, very different size. So that's a trivial example. But in fact, you have a much more interesting example, which is given by nil manifolds. So the non-trivial example is this nil manifold example, which is the classical example to first read or understand when you start thinking about n structures. So you look at the Lie group, a certain group of upper triangular matrices that are given by 1 on the diagonal, 0 below, okay? And you might have some coefficients above. So this Lie group is so-called nilpotent in the sense that if you take commutator of n with itself and you repeat that, you take commutator with n again, and again, you get 0. So n is nilpotent. In the sense that when you do this enough time, when you take commutators enough time, you will get the trivial group. And that is called the nilpotent group. Anyway, now let's look at the Lie algebra of this Lie group. The algebra of this Lie group is going to be, okay, you have 0 everywhere and you have some coefficients above. Whenever you are in the strictly upper side of your matrix. And you want to put a metric on your Lie group n. In order to do that, you just need to put a metric on the Lie algebra, so the tangent space of n at the identity, and then you push this metric using the action of n over itself, and you get the left invariant metric. So that's the plan. Let's define a metric for this Lie algebra G. For A in the Lie algebra, you look at the following metric that is going to depend on a parameter. So this is our metric. Where you take the sum of the squares of your coefficients of the metric, but you weight it using a power of delta. That depends on how deep you are in the matrix. Delta is a positive number. And Yeah, so once you have this metric at the identity, meaning on the Lie algebra, you get a left invariant metric on N automatically. Okay. Automatically. So for such a metric, it is known by computation that the sectional curvature is determined by the Lie bracket. So for such a left invariant metric, the sectional curvature is given in terms of the Lie bracket, is determined, it's better maybe, determined by the Lie bracket. Meaning, if you can compute the Lie bracket, then I can give you an expression for the sectional curvature. One reference for that is there's this old paper of Milner on left invariant metrics. So see, for example, Milner. Anyway, but here, it's everything is explicit, and you can check that here. If you look at the Lie bracket of two matrices, A and B, that are in the Lie algebra, in fact, you have that it's upper bounded by a dimensional constant times the corresponding norms of A and B. Sorry. All these norms are depending on delta. Delta is right now fixed, but we're going to send delta 0 to 0 later. So in order to check that, well, let's look at, for example, a product for, say, AB. So AB is the product of Ij, B, KL, and it's going to be the sum over M of A, I, M, B, M, J, or 8. So if you compute the norm of that guy, it's going to have the form that I'm writing here, square, and the delta to the power 2 GI. But you see that because of the scaling here by delta to a certain power, it plays nicely with products. Delta to, say, M minus I, G minus M. And so you get that whatever you want. So because of this inhomogeneous rescaling by delta to a certain power, you get a nice behavior when you take products, and in particular when you take Lie brackets, you get that the Lie bracket has norm bounded by the product of the norms, but that implies that the sectional curvature is upper bounded by a dimensional constant. So all this computation, what it is giving us is that the sectional curvature of your metric is bounded by 1. So sectional curvature is bounded by 1 by explicit computation. Sorry, not bounded by 1, but dimensional constant. And moreover, remember that we're rescaling by delta. So delta is going to be is going to be very small. You can get examples of collapsing metrics, compact manifold that are collapsing by taking compact quotient of your B group N. Okay. Metric. For instance, N quotiented by gamma, where gamma is this co-compact lattice given by integer coefficient matrices. Gamma is a co-compact lattice of N given by integer matrices of N. Integer subgroup of N. So why is that example interesting? It's because you have that the diameter of the whole thing is going to 0. Because remember, because of the form of the metric, and the sectional curvature is bounded, so you're collapsing, and you're even stronger than collapsing, your diameter is going to 0. However, this manifold does not carry a flat metric because of Weber-Bar. So Weber-Bar tells you that flat metrics are always finitely covered by flat tori, and this is not the case for this particular quotient N over gamma. So much. So the sectional curvature is bounded by, say, a dimensional constant, and the diameter is going to 0. So, so that is called, such a manifold is called almost flat by Gromov. So, almost flat. But cannot be flat. Cannot be flat due to Weber-Bar. I'm going to use 5 minutes to tell you what's going on next. So this example shows you that really only talking about F structures is clearly not enough to describe what's happening in general. So in this case, you have this nil manifold that is also collapsing with diameter going to 0. So clearly, those kind of manifolds won't play a role. And in fact, you have the following Theorem of Grimoth, and I'm going to finish with that. And that's an essential theorem if you want to understand N structures. That's one of the building blocks. The Theorem of Gromov was later improved by Roux, and the main theorem says that if you're an almost flat manifold, meaning there exists a sequence of metrics with sectional curvature bounded, but diameter going to 0, in particular, the injectivity radius is going to 0, is finitely covered by a nil manifold. And Roux improved it by saying, okay, this is not any finite cover. You have some structure for this cover. Let's not get into that. What's important here is that any manifold such that you have a sequence of metrics with bounded sectional curvature and diameter going to 0 is given by a quotient, finite quotient of a nil manifold. And we will see next time that those manifolds, those nil manifolds, are playing the role of tori for F structures. So, N structures, sorry, let's see. right structure. Let me compare a little bit. You have tori, they play a fundamental role in the definition of an F structure, while for N structures, what's going to play this role is going to be those nil manifolds. So instead of having an abelian structure, we have a nilpotent structure. And moreover, so the theorem of Bieber-Barr is going to be replaced by a theorem, this theorem of Gromov, giving you the structure of almost flat manifolds. And we'll see that N structures are essentially given by actions by nil manifolds that can be glued together in the same sense that F structures are tori actions that you glue together. This is what I wanted to say today. So thank you for your attention.
Thank you, Antoine. Thanks for this lecture with lots of examples, which are very useful to us. So are there any questions? Okay, I don't see questions on the chat, and in the room, people are more or less very quiet.
Mm-hmm.
So I thank you very much, and we meet again tomorrow for your last lecture. Same time.
See you tomorrow.
Laurent has a question.
The link doesn't seem to work.
Yeah, we were not able to.
Okay. Okay. Thank you for telling me. Okay. Next time I'll try again.
Okay, very good. Thanks a lot. Thank you.
Yeah. Thank you. Bye-bye.